Welcome back to HCS5887. We're continuing with our third module on covariance. In this case, we're looking at one additional example in which we use R, in this case, to program covariance, and we'll look at the effects of the covariance analysis on the actual output. Just as a refresher, we will use covariance for two possible situations. We can use one or more variables. We call these covariates to control or reduce experimental error. When we reduce the experimental error, we reduce the error degrees of freedom and have a better chance of a higher F value and a significant effect for our treatment effect. We also will adjust the means so that they'll be compared at the same level of the covariate, and to do this we use LS means in both R and SAS. You might recall we had used LS means earlier in the semester when we were using to adjust a mean based on it having a missing value, and because of the potential for bias in the interpretation in a block design, especially where we generate new values for the means that could be predicted, the mean that would have been predicted if we might have had a value for that particular block. In this case, we're using LS means. We're adjusting the means, in this case, to the same level of the covariate using a regression model. So in this example, we're looking at a study that measured the growth of 80 beef steers on 4 diets varying in the level of protein. The 4 treatments, in this case, are a control, a diet that is 14% protein, a diet that is 18% protein, and a diet that includes alfalfa. Steers began the study as weaned stockers in the beginning of the season, and their weight was measured 300 days later once they were at market weight. There were 4 treatments and 4 replications in a completely randomized design. Each experimental unit was the average of 5 steers. And for example, here we could see these 5 steers are all in the same pen and they are being fed the same diet. So we do have subsamples, although we're not going to consider the subsample effect. We could have a covariance model and include subsamples if we wanted to conduct that analysis. The experimental unit then is the average weight of those 5 steers. In animal science, very sensitive to the issue of that steers with different weights will grow at different rates. In general, larger steers will grow faster than smaller steers. And so, as is the case in animal science, is that they were careful to balance the treatments for the initial weight of steers. And so by having the starting weights, the composition, the 5 steers that composing a experimental unit were carefully selected so that each experimental unit started with 177.5 mean weight of steers, balanced across the treatment. But with the limitation of the experimental material, the weight did vary slightly among the experimental units. So our data might look something like this. Here we can see the 4 treatments, the control, the 14% protein, the alfalfa, the 18% protein. We can see the body weight in kilograms at the end of the study, the response variable, the weight after the experiment, and BWI, the initial weight prior to the start of treatments. If we were to average the 4 initial starting weights, each treatment would have the identical initial starting weight, 177.5 kilograms on average for each of the treatments, but each experimental unit there is a slight difference in the weight across the experimental units. So let's look at the analysis initially with the covariate excluded, and that is the top piece of code, and then the effect with the experimental unit included. So we create the variable AOV.out. We use the AOV command, and the model statement then is the body weight at the end of the study, tilde, and being a completely randomized design, treatment is the only effect in the model without the covariate. We can see the effect of treatment then generates an F value 3.3 with 3 and 12 degrees of freedom, which has a probability of 0.0571, a non-significant result. However, some component of the variation was the result of different body weights at the start of the experiment for each of the experimental units. And when we add body weight initial into the experimental design, we can see that there's quite a large contribution to the sums of squares. And because the body weight had been balanced across the treatments, the mean treatment effect in this particular case is absolutely identical, sum of squares of 7208. But we can see that the error the 8704 has been partitioned into a component due to true error and a component due to the starting weight, the different starting weight of the animals among the experimental units. The benefit then in this case is with the smaller residual mean square. Now we can see the F value is larger and the probability less than 0.05, we can see that there is a significant effect of treatment on the in this study. We can also see a significant effect of body weight, which adds evidence to the value of including initial body weight as a covariate in this model. So notes, treatment sum of squares and mean square are identical with and without the covariate in this case, specifically because the weights had been balanced across the treatments. And significant changes, we now have a significant result because the error is smaller. Let's look at the least square means. Using t-apply, we're calculating the arithmetic means. We can see the arithmetic means for alfalfa 475, control 441, the P14 is 464, P18 500. In this case, you'll notice that with LS means we get the identical results. Alfalfa 475, control P14 464, P18 500. And since the initial body weights were perfectly balanced across treatments at the beginning of the study, here we see no change between the arithmetic means and the least square means. So in this particular example, the benefit of the covariate has been in changing the significance to the experimental result to one of significance, whereas without the covariate would have been non-significant. So this example contrasts with the prior example with the yields, where we didn't see a change in significance. It was significant with both the covariate and the covariate, but we saw a radical change in the ranking of treatments. In this particular study, the opposite result. Significance changes from one of non-significant to significant, but we see no difference in the ranking of treatments. So covariates can have a range of different purposes depending on the nature of the study, how it's been set up, and what the actual effect of the covariate was. Before we conclude this example, just want to look at a couple more possibilities that we have in how we could analyze covariates. This data actually allows an alternate analysis. Rather than using the final weight as a response variable, that is BWI as a covariate, another option is to calculate the net increase in weight as the response variable. That is to say, we have the body weight is the weight of the animals after 300 days on their respective feeds. We have the body weight initial, the weights of since the experimental unit is 5 animals, it's the average weight of 5 animals in the experimental unit. We can actually subtract the difference and we can look at the live weight gain during the study so that our response variable is not the final weight, but the weight that the animals actually gained during the study. In this case, we would not use the covariate. The starting condition has been accounted for in terms of the weight of the gain of animals during this 300-day period. And here we can see that live weight gain is the variable that we do have a significant result of treatment when live weight gain is used as a response variable, or that is to say the starting condition has been calculated into the treatment effect. This approach might not work for all studies. In this particular case, the covariate is a variable of similar magnitude and units as the response variable. In many of our cases, the covariate will be a completely different data and wouldn't lend itself to analysis in this particular way. Going to stop the share here just for and we'll go on to the second example in the next audio.